let us discuss one of the important distributions. It is known as multinomial distribution. This is a discrete distribution, and discrete multivariate random variables follows a multinomial distribution when if suppose you are taking a responses which is like having more than two categories. For binomial cases we discussed, this multinomial distribution is a extension of the binomial distribution. So when if we consider that these responses having more than two category, for example, if we consider in a pond, suppose there are fishes, different type of fishes. For example, hypothetical example is that suppose if you consider color, different color of fish, maybe red or yellow. So just a hypothetical case, or you can consider some balls. So now if there are two category, suppose if you are considering like one is red category and another is suppose black, any. So then this kind of responses, it is known as binomial responses. So suppose a random experiment you are doing, for example, very simple case we consider as a tossing a coin. So there are two category only, one head or tail. So in that case it is called a binomial responses. Now if there are more than one category, more than two categories, so for every random experiment, every observation, so there are more than two categories. Suppose in a pond, suppose there are four category fish, so there may be blue and some other color, maybe yellow, red, blue, white, so maybe any of the color. So now suppose n number of fishes you consider, then suppose there are n number of red fish, n2 number of black fish, n3 number of blue fish, and n4 number of white fish. But that n1, n2, n3, n4 are totally random variables. These are the observation of a random variable. Suppose y1 is the random variable, it is the category 1. y2 is the random variable if it is category 2. y3 is the random variable if it is category 3, and y4 is the random variable, it is category 4. So then we define that if so y1 is equal to 1 if red fish observed, suppose if we draw one fish from the pond, and then if you see that this is red fish, then we denote y1 equal to 1, otherwise 0. Any other cases it is 0. So then this variable actually defined this red fish. So then y2 is that random variable. Similarly it is defined that it will be 1 if suppose a black fish observed, black is a fish is observed, so otherwise it is 0 otherwise. So similarly other variables also defined. So note that, so there may be they may not be independent, because so if there are whenever you are collecting fish, how many actually fishes are there we don't know. So based on that, some of the experiment earlier also we discussed, so it may be they are dependent or they may be independent also, but we have to check that from the distributions. Now in this case what we are discussing, most it can be considered both the cases. So now let us discuss here more general way. In an experiment there are k possible outcomes labeled A1, A2, AK. So for example here 4 possible outcomes: red, black, blue, and white. All are mutually exclusive actually. So if red observed, then black or blue or white cannot be observed. So each outcome has a probability of occurrence pi. So whenever you are collecting a fish, suppose one time you collected, suppose then that probability that y1 will be 1 is p1. So that is the assumption. So because we don't know exactly how many fishes, if we know all these things, so then we can find some probability, but usually we need to estimate from the data, but here we are assuming that it is known. So then what is the probability that red fish may be observed? So then probability that this y1 is equal to 1, this may be p1. Probability that y2 is equal to 1, this may be p2. And probability that y3 may be 1, this may be p4, and probability that y4 is equal to 1, this may be, sorry, this is p3 and this is p4. So there are 4 possibilities only. So that's why because whatever phase it comes, it will be one of them. So because this is the assumption that in the pond, suppose this is the red, black, blue or white maximum. So they are mutually exclusive and also exhaustive. So all the pieces are all this type only. This is the assumption. So in that case, this probability will be P1 plus P2 plus P3 plus P4, that should be is equal to 1. Now the experiment is repeated n times. So whenever you are drawing the fish one by one, so then n times repeated means n number of times, suppose n pieces we catch, and then let xi represent the number of occurrence of outcome ai. So here actually I denoted yy. You can consider for, because it is given here. So this is x1 and then this is x2, x3 and x4. It is denoted like this. So it is there nothing, no, you can use y1 also, it is just a variable, so that we just in our discussion we should not have any confusion. So because we denoted here x1, x2, x3 and x4. So x1, x2, sorry, this is x1 is equal to 1, x2 is equal to 1. So now P1 plus P2, P3 plus this should be is equal to 1, and define the random variable x as the multinomial random variable. It has parameters like this. So this is known as multivariate random variable. This vector x1, x2, here actually four variable only, x1, x2, x3 and x4. So 4 variate random variable, and we denote this by it has a parameter like multinomial random variable with parameter, because n how many times this random, that like here n pieces we drawn. So this parameter n, how many number you are taking, and then P1, P2, like here actually 4 only, P3 and P4. So then what will be the probability mass function, that we have to find. So this will be a multinomial distribution if it has some particular probability mass function. So let us recall the binomial distribution cases. So binomial distribution cases, each trial random experiment we are repeating n times, we have only 2 categories. So either here yes or here no, only 2 category, like blue or black, like that. So now we assume that, suppose let us assume that each y1 is the first time you are drawing, and or for simplicity let us consider y is the random variable. Y is equal to probability that y is equal to yes, this is 1, this may is with probability p, and probability that y is equal to 0, it is 1 minus p, and you are repeating n times. Then what will be the okay, so that's why I just wanted to make it yi. So ith time, whenever ith time you are repeating this observation, repeating the experiment, so for each time it is a Bernoulli random variable, and this y will be how many times this yes come. Now this y can be is a binomial distribution, we say NP, if this probability that this y can be taking some value y, it can be given as NCy p to the power of y 1 minus p to the power of n minus y, and whenever y can be taking 0, 1, 2 up to n and 0 otherwise. So this is, you can recall that this is the binomial distribution. So let us start with this binomial distribution. We not require this concept now. So we have already learned these things. Now we just start with, suppose y n times we repeated these things, and then y has binomial NP. Now this probability mass function, so this is p of y. So then actually this y you are considering how many times it has yes. So n times we repeated, repeated this trial random experiment, then we found that this y is yes and n minus y is no. So that is the probability we want to find. Suppose let us denote this y by y1 and n minus y by y2, such that y1 plus y2 will be n. Also this random variable that yes it is coming, this category, let us denote by y1, and no it is coming, this category is y2. So please forget about this previous notation, otherwise it will be confusing. So this y1 and y2, so yes and no. So then what will be the probability that y is equal to y, so these things actually is equivalent to nothing but probability that y1 is equal to small y1 though, and y2 is equal to small y2. So here probability that y1 can be for one trial or one so once you are taking the trial, so this is probability that it can be p1, and probability that y2 can be, suppose n is equal to 1, so in that case it is a Bernoulli random variable only. So then y2 will be is equal to 1. Basically here y1 and y2 it can be just a they are opposite. So y2 can be 1 means this category. So this means nothing but this, it may be 0 observation. So this is nothing but p2. So that p1 plus p2 is equal to it is equal to total 1. So basically if you compare with our previous notation, p is nothing but p1 here, and 1 minus p is nothing but p2 here, and y1 is that whenever y is the random variable taking 1, and y2 is that whenever 1 minus y taking 1. So y2 is nothing but 1 minus of y. So that's why y2 will be 1. So y is taking 0. So in that case, suppose n times we repeat it in now instead of 1, if we take n time repeated, what is the probability that this capital Y1 will be Y1, that means number of yes will be Y1 and number of no will be Y2. So this probability actually, if you, so this is nothing but same as we are talking about the previous random variable y taking this value y. So this is now NCY. So now NCY how we represent? So this is n factorial, then this is y factorial, n minus y factorial, and p to the power y. So p is become p1 and this is y1. 1 minus p become p2. Now whole to the power n minus y will be number of no, this is y2. Whenever y1 and y2 can be any value between 0 to 1 n, and y1 plus y2 has to be is equal to n, otherwise 0. Now if you here we want to make it more clear, suppose this is n factorial by it is y factorial means y1 factorial, and n minus y means y2 factorial, and then p1 to the power y1 and p2 to the power y2. y1 and y2 can take the value 0, 1, 2, take the value 0, 1, 2 up to n, such that satisfying y1 plus y2, satisfying y1 plus y2 is equal to n, and it is equal to 0 otherwise. So this is the actually it is just a same probability mass function in a different way we wrote. Why we wrote? Actually the reason is that it should be we can easily generalize it for the category whenever it is not more than 2 categories. So in the multinomial random variables. Now for binomial cases, whenever we say it is binomial cases, so then this probability mass function written in this way. So let us now find these multinomial cases, how this probability mass function can be represented. So multinomial cases, we have some more than 2 categories. So like category 1 up to, suppose q number of categories are there. So let us see that what is the notation it has followed. K number of categories they have considered. So 1, 2, k. So this is the random variable y1, if it is y2 for category 2, and this is yk, and the probability that this category can be 1, this is probability p1, this is p2, and this is pk. So summation of pi, I is equal to 1 to k, this is equal to 1. Now we are talking that what is the probability that suppose n number of times, n times it is repeated, this trial n times repeated. So then what is the probability that this capital Y1 will be small y1, capital Y2 will be small y2, and capital Yk will be small yk. So what is this? What does it mean? Suppose n times we repeat it, so then how many times? Suppose n number of pieces we caught, and then what? How many pieces like with black pieces will be? How many pieces will be in blue? So that we want to know. So y1, y2, yn will be n number of fees will be related with total category fees. This will be yk. This will be is equal to n. This is. So then this probability, so you can see that we can extend directly from this binomial case. So this will be nothing but n factorial into the by y1 factorial, then y2 factorial, then yk factorial, then p1 to the power y1, p2 to the power y2, then pk to the power yk, such that y1 and y1, y2, yk all are belongs to 0, 1 to n, satisfying the relation yi, I is equal to 1 to k, this should be equal to n. Otherwise, this probability is 0 for any other cases. So this is the probability mass function. You can see that we just wrote this binomial distribution. It is 2 category only. We extended to the k category. So it is known as multinomial random variable. So then here it is represented. You can see that a multinomial distribution. The probability mass function of the multinomial random variable x is given by probability x1, x2, xk, or x1, x2, xk is nothing but n factorial by x1 factorial, x2 factorial, xk factorial, p1 to the power x1, p2 to the power x2, pk to the power xk, such that summation of xi should be equal to n. x1, x2, xk can take any value between 0 to n, but summation of xi has to be equal to n. So this is known as multinomial distribution function. So it is a little because it is a multivariate case, so it will be little complicated. So we will not go through more details about this. We just learn it in the future whenever it will be needed. We will discuss more. So let us discuss what are the applications of these multinomial random variables. So some of the applications. So it is used in clinical trial. So whenever you have more than one category in your responses, suppose a disease can be classified into the severity of the disease. It may be disease presence or absence, then it is 0 or 1, but it may be classified into suppose what is the suppose cancer. So this disease there may be stage of the cancer, so it may be there is no cancer, or maybe first stage or second stage or third stage. So in this way you can different category you can define, or you are giving medicine, so there is a adverse effect of the medicine, or it is known as some toxicity effect of the medicine. So this can be categorized into 2. Then it is a binomial responses, like either there is a side effect or adverse effect, or there is no adverse effect. So but it may be classified into more than 2 categories also. So like what is the severity of the adverse effect, like it is no adverse effect, or mild, or average, or very severe, or death maybe. So then we can classify into 5 categories. So then we have to use the multinomial distribution function. So chess game prediction also it is used, opinion polls of election, because opinion polls there will be more than 2 candidates or different actually different type of posts. So then we have to consider this multinomial distribution function. Number of different category, actually opinion poll is different party. So like so different in the opinion poll, if there is 2 only, then it is a binomial. More than 2 means it will be multinomial. Number of different category pieces in a pond that we discussed. Basically anything you can think of that can be different categorical observation, then you can use the multinomial distribution. So multinomial distribution is nothing but a extension of the bivariate cases like binomial distribution case. So this is one example we discussed. This is known as the multinomial distribution. So next we will discuss one example for multivariate random variables in the case of continuous. So continuous multivariate random variable. So we will discuss. It is known as multivariate normal distribution. A q-variate random variable x is called a q-variate normal random variable if its joint probability density function can be represented in this way. So it looks very complicated. So let us discuss first, if you can remember, what is univariate normal distribution. So let x be a univariate. So let us for univariate we may not mention it, be a normal distribution. Let x has a let x be a normal distribution, normally distributed random variable with mean. So we know that this parameter mu is nothing but mean mu, and the another parameter, it is nothing but variance sigma square. This is always greater than 0. Now mu can be any real number. The probability density function of x is given by, so how this whenever it is univariate random variable, probability density function of x is given by, so f of x, this is 1 by root 2 pi sigma e to the power of minus x minus mu whole square by 2 sigma square, whenever x is greater than minus infinity, less than infinity, 0 otherwise. So this is the probability density function of a univariate random variable. So you can remember this. Now what is mu? So mu here nothing but the mean of the random variable expected values of x. And what is x? Sigma square. Sigma square is expected values of x minus mu whole square. So this is the two parameter. Now for a, if we consider a multivariate random variable, let us consider a multivariate random variable suppose this x, suppose it is, what is the dimension it is considered, let us follow that q dimension. So x1, x2, xq. Now if you want to extend this to q dimension, then this parameter also we need to know what will be these parameters. So whenever it is q dimensional random variable, how this expected value it is defined. So expected values of x, it is expected values on a vector x1, x2, xn. So it is defined on, so it is q variate xq, it is defined as, it is a, because all are random variable, so we can define expected values of x1, expected values of x2, expected values of x key. So these are all real number. So let us denote expected value of x1 is mu1, expected values of x2 is mu2, expected values of xq is mu key. So let us denote this mu tilde. So it is a vector. So expected values of x of a multivariate random variable, it is nothing but a vector and it is in RQ. Now next is that what will be the variance. So in that case of univariate case, it is just a one single number x minus mu whole square. Now for multivariate cases, we will consider the covariance. So covariance of, we say covariance of the random variable x1, x2, xk. So the how it is defined, actually we need to consider all possible combination of the covariance. So two at a time, if you NC2 if you consider, so then it will be a matrix like this. So this is first, it is covariance between x1 with x1, so it is nothing but variance of x1. So covariance between x1 and x2 like this, covariance between x1 and xq. Now next, covariance between x2 and x1, then covariance between x2 and x2 like this, covariance between x2, xq. So covariance between xq and x1, covariance between xq and x2, covariance between xq with xq. Now then this is denoted as, we denote by sigma sum. It is just a notation only. So now what is the covariance between x1 and x2? So let us, so any covariance between, we know that xi with xj, so it is nothing but expected values of xi minus mu I and xj minus mu j, and it can be simplified to, so we denote by sigma ij. So this is, it can be simplified to expected value of xi xj minus mu I mu j. Where mu I mu j already we denoted by their means, I random variable. So sigma ij is this. So if I is equal to j, so if I is equal to j, so suppose sigma I, so we say sigma I square. So basically by this notation, sigma I, so this is covariance between xi with xi. So this is by definition expected values of xi minus mu I into expected values of xi minus mu I. So it is nothing but expected values of, this is equal to expected values of xi minus mu I whole square. So this is nothing but the variance of the ith. So this is, it can be noted that this is sigma I square, ith random variable. So then this sigma can be represented as, like sigma 1 1, sigma 1 2, like this, sigma 1 q, sigma 2 1, sigma 2 2, sigma 2 q. This is just a notation, q1, q2, sigma q q. So this q q, these are all variance. So we can write sigma 1 square, sigma 1 2, sigma 1 q, then sigma 2 1, sigma 2 square, sigma 2 q, like this, sigma q1, sigma q2, sigma q square. So this is the variance. So it is known as the variance covariance matrix of, variance matrix of multivariate random variable x, x1, x2, xk. So this sigma, it is known as, the sigma is known as variance covariance matrix of x. Now we understand that in the univariate cases, what we say, the mean and variance. For multivariate random variable case, this should be this vector mean mu, and the covariance matrix, it will be a, so the variance, it will be a covariance matrix sigma, capital sigma. So it is assumed that, so for example here, for univariate cases, mu can be any real number, minus infinity to plus infinity, any real number. But in this case, sigma square will be greater than 0. But what about multivariate cases? Multivariate cases, it is assumed that for multivariate normal distribution, it is, whenever we will define, we will see that it is needed also that this is a positive definite matrix sigma, and mu is any real number, any Rn, Rq, it is a Rq, but sigma has to be a positive definite matrix. Variance covariance matrix is a positive definite matrix, we need it. So now we let us go back to the probability density function for univariate cases. So if x has normal mu sigma square, so we will see that how we can generalize it for the multivariate random variable. So whenever x is normal mu sigma square, the probability density function of x, is given by f of x, it is 1 by root 2 pi sigma e to the power of minus x minus mu whole square by 2 sigma square. So that can be represented by 1 by 2 pi whole to the power 1 by 2. Then sigma we can replace by sigma square whole to the power 1 by 2. Then e to the power of minus. So this can be represented 1 by 2 and x minus mu sigma square minus, it is the inverse of sigma square, 1 by sigma square, it is a real number only, x minus mu. Because x minus mu is a real number, we can consider it as a 1 cross 1 matrix. This transpose will be same, so we just writing it in this form. So that just will be, now we can extend it to the, this form we can remember. This is just remembering to understand it, how univariate can be just representation purpose only. The multivariate, the PDF, the probability density function, joint probability density function, the joint probability density function of a multivariate random variable x, x1, x2, xq, sorry, multivariate normal distribution of a, not only random variable, it is a normal multivariate joint probability density function of a multivariate, or we can say q variate, of a q variate, because it is q number of variables are there, q variate normal distribution x joint probability density function of a q variate normal random variate q-variate normal distribution x is given by, so this is f of x. So we are writing in a short notation, x tilde means x1 x2 xk. So q-variate normal distribution x is given by, so see that because it is q, we will write that. So here you can see how it is represented. Here it is 2 pi. Okay, so there may be a mistake because this here nothing n is there. It will be represented only because it is q. So this will be q. 2 pi whole to the power q by 2. This will be this 1 by 2. It will be 2 pi whole to the power q by 2. Now sigma square here it is a univariate case. This is just a real number, but for multivariate cases we have this variance covariance matrix sigma. So this sigma is here. So we will take the determinant of sigma because by assumption it is a positive definite matrix. Determinant of sigma is always greater than 0. This is sigma to the power 1 by 2 e to the power of minus 1 by 2. Then this will be our vector x minus mu, then whole transpose, then sigma square it will be a variance covariance matrix sigma inverse, and then x minus mu whole transpose. Sorry, it will not be transpose. So basically this is actually q variate. So this will be q cross 1, and this is q cross q, and this is 1 cross q. So then this will be a real number, 1 cross 1 a real number. And okay, so this is known as the density function, joint probability density function of a multivariate random variable x. So now we have understood that what are the significance of this parameter mu and sigma. So mu I is nothing but the expected values of the xi for I is equal to 1 to n q, and sigma is nothing but sigma is the variance covariance matrix of x. So that we have already discussed, x1, x2, xn, xq. So now we will not discuss here multivariate normal distribution. It is little complicated because we are considering multivariate random variable. It is not as simple as univariate cases. So just to remember that whenever you are considering a univariate distribution, then this density function looks like this. So this is now for multivariate cases it cannot be represented. It will be so you can understand that whenever we see some of the hill station like that. So some of the hill. So this is we say some kind of shape actually. Somewhere it is increasing and it is coming to the some of the peak, and then it is decreasing, and mostly at that peak it is the nothing but the mean, and also this is mode, and this is the median of the normal distribution, and then both side it is symmetry. So these are the properties. So similar kind of properties can be shown in in a multivariate cases also we can find the similar type of properties. So what are the application of these multivariate random variables? There are many applications, like whenever you are considering many variables, many different responses you are considering to model. So then suppose application in different field of studies considering multivariate observation. In the following study, data was collected for a sample of n is equal to 183 females on the variables. Suppose some of the variables are maybe age, height, weight, cholesterol, albumin, calcium, uric acid. So these are 1, 2, 3, 4, 5, 6, 7. So 7 q is equal to 7. So this is all the variable they may be univariate consider. So it is a univariate normal distribution. All the variable mostly these are normally distributed random variable. But now if you consider together as a vector, so then because they may not be independent, because age and height they may be related, correlated, and weight and height also they are related. So all these values like cholesterol and weight, they are maybe related. So we cannot consider that these are univariate random variable and they are independent, and then we just multiply to find the multivariate distribution function or multivariate density function, as we consider some of the examples. So here, because they are not independent random variables, we need to consider correlated random variable. In that case, we need to use this multivariate normal distribution. So this multivariate normal distribution, it is given here. So this is some because we discussed some of the multivariate random variable cases, some numerical example we discussed, and here some of the important distribution. In discrete cases we discussed multinomial distribution, and for continuous cases we discussed multivariate normal distribution. Hopefully you have followed that. So next we will discuss some different topic. So this is known as transformation of random variable. It is very important topic. Let us go through the transformation of random variable.